Okay, Zhitong, you can start.
All right. So hi everybody. So today I will talk about high-dimensional Bayesian optimization. So if there's any questions or like anything like you think is interesting, you can stop me like immediately and we can have a discussion. Okay. So for the layout today, I will first give an introduction of the common approaches to high-dimensional Bayesian optimization, and then we can dive into the first paper. Although it is a paper on the Gaussian process regression, but I think it's kind of interesting and it have like a lot of insights for Bayesian optimization. And then we can have some background for learning the decomposition with additive model, and then we can go through the second paper, and then we can have a discussion. I really think the paper 1 and paper 2, they are trying to tackle the same problem, but with different ideas. Okay. So for the common approach to high-dimensional Bayesian optimization, it's kind of like based on the assumptions. So the first kind of like approach is like they assume there's a low-dimensional structure or like a linear projection. So the most famous paper are Rainbow is a really old one. It's stand for the random embedding Bayesian optimization. And Alibo is kind of like built upon Rainbow, and Sasbo is kind of stand by itself. So it has it plays a sparsity reduced prior. So the main idea of this approach is it assumes there is a projection matrix called phi that transforms the high-dimensional input space into a low-dimensional subspace, and we're gonna learn a function.
Wait a second. You need to first introduce what is Bayesian optimization.
Oh,
why I mean, directly apply BO for high dimensional problems will fail.
Oh, okay. So okay, so sorry about that. I saw like everyone is like, okay, so Bayesian optimization is kind of like a way to do the non-convex optimization, where it's like they use a surrogate model to model the data, and they use a acquisition and they maximize the acquisition function to get the next query point. So this is the loop for the Bayesian optimization. So they continue the loop and we get new data points every iteration. So in high-dimensional Bayesian optimization, why it's gonna fail? Because for the most cases, they cannot learn a good surrogate model. So it's not always. So it's always like we don't have the good surrogate model.
Yeah. Okay. So if you have some marker, you can draw the. Yeah. So let me give a brief introduction. So the problem setting is like, okay, I want to maximize or minimize. Let's use maximize a black box function f of x. Right? So black box function means that you don't know the exact form of f of x, right? And you don't know how to calculate the gradient of f of x, right? Then how do you maximize this function? So there are many applications associated with this problem. For example, hyperparameter optimization, right? So you know that the neural net, the length, the width and depth of neural networks, or the choice of the learning rate, have a substantial influence on the generalization performance, right? But you don't know what potentially the expression is useful or is true to characterize such relationship. Okay? Or in many design optimization problem, like when I adjust some properties of the materials, then some kind of like quantity of interest, like maximum load, will vary as well. And you don't need you don't know what is the functional form to represent this kind of mapping, right? So there can be some numerical methods to compute that. For example, you can try to solve a set of equations by using numerical methods, but you just can't come out some kind of symbolic expression to show their relationship. So yeah, so that's basically what Bayesian optimization tries to address. So the idea of Bayesian optimization is to construct a surrogate model, a probabilistic surrogate model to approximate F. So at the beginning, you only have a few data points, maybe 5 or 10 data points, where you maybe randomly pick up a set of locations x1 to x10, and you're gonna have some observation over fx1 of fx10. You're gonna use that to construct a probabilistic surrogate model. Typically, it's Gaussian process, right? And Gaussian process, from its posterior distribution, it can tell you which of the next location it has the best potential to examine. Okay, so it's an iterative procedure, like you query more and more function values, so your surrogate model get more and more accurate. At the same time, yeah, from the posterior estimation of the functions, like in GP, you get to know which point are more closer to the function maximum. This is like active learning, but the goal now is trying to search for the maximum or minimum of the function. The problem is that when your input dimension, like x, is very high dimensional, like 100 dimensional, usually Gaussian process will fail. We know that Gaussian process only works for low dimensional space. Okay. So I think one meaningful topic, or very important topic in Bayesian optimization, is to address the high dimensional Bayesian optimization problem. That means we need to modify Gaussian process model itself and make it more effective to capture the function landscape as to the high dimensional input space. Yeah, Zhitong can go ahead.
Thanks for that. So RANBO is kind of like stands for the random embedding for Bayesian optimization, and ALIBO is it's built on the RANBO, and SASBO is like a different class. It's use sparsity induced prior on the landscape. So the main idea is like the high dimensional input space. We want to have a linear projection, the phi, to project into a really low subspace, and we use the Gaussian process to approximate that. So what is the failure mode for this kind of like approach? So the function, the black box function fx, may not always have a low dimensional structure. Like for example, the Rosenbrock, every dimension is important, and even if they have a low dimensional structure, and always it is sensitive to the choice of D. So what is the dimension of the subspace? So one example is like RANBO has a really good like theoretical guarantee, but always feels like empirically. It had due to the poor GP fit. I put a picture from the paper of ALIBO, where it like depicts the Gaussian process GP model, and compare it to the actual function. So you can see the RANBO learns really bad GP. And the second approach is using the structure decomposition. Usually it's the additive structure. So it assumes like the high dimensional function can be decomposed into a sum of low dimensional functions. And like each functions, we assume that it is going to be a Gaussian process. Okay, so the failure mode is like additive structure is usually not a realistic assumption. And learning the decomposition is hard. We were going to dive into why the decomposition is hard to learn. And the third approach is the local optimization. I think this is a kind of like really like different approach. It's called it's called TURBO. It stands for the trust region optimization. Trust region Bayesian optimization is similar to the trust region optimization in like our convex optimization. So the main idea is to restrict where the acquisition function is optimized to avoid the over exploration. So the TURBO didn't make any assumption. It didn't assume there's a low dimensional subspace. It didn't assume there is a structured decomposition. So TURBO gonna convert really slow, and it is designed for like high throughput setting. Okay, So let's go through the first page.
One thing, Zhitong. So does Turbo also use standard Gaussian process for surrogate model?
Yes.
But how does their GP model work for high dimensional inputs?
So, but only for a small region.
What do you mean?
So kind of like, I think what they do is kind of like they optimize in a small region. So like the trust region optimization. So they kind of constrain the region they are going to optimize.
So you mean they just pick up a small subset of inputs to construct GP?
Yeah, so they kind of put up like optimization bounding.
No, I think the trust region is not picking up the subsets of the variables. It's pick up all the variables, but in a very small hypercube.
Yeah.
Or sphere.
But how do they construct GP? The GP is still based on all the variables?
Yes.
Yeah.
If it's still based on all the variables, how could it work?
I think it's like so I read a paper is like they put in a small region and they collect more like, so they don't like do the over exploration on the other part. So they only optimize like a certain area, like a certain sphere, like in the all with all dimensions, and then when like they yeah, but they always use the GP, but always restricting the space, not the input dimension.
Yeah, I'm not clear. Like if you can restrict the range of the variables, like you put it a small hypercube, right? But the GP is still placed on the function of all the input variables, right? So
Yeah,
it's like compute the kernel function between like two, say 100 dimensional input variables.
Yeah, so that's why like I think like in the like more like recent paper, like they always have better results than Turbo.
I think the intuitive here is since the high dimensional, you're using a standard GP to model the high dimensional outputs is poor, so they don't want compute the acquisition function of the entire input space. They just want to explore a very small region instead.
Very small region means a subset. I mean,
No,
just a subset of inputs, or
no, it's not a subset. It's a very small hypercube at some well existing optimal point, probably.
and then when you add a point in that region, you can still drive GP to learn.
Yeah, so they're gonna have like a lot of points built up in that region.
A lot of what?
A lot of acquisition points from that region. So they're gonna have like, so they are having like more and more points in that region. So once they are confident in that region, they search another region.
Okay. Yes. So yeah, you better make clear about how this turbo work, because our experience shows that if you have a very high dimensional input to the GP, like if you use say Gaussian kernel, the landscape doesn't change. It looks like very hard to learn the GP model, right?
Yes. So I will double check on this and get back to you after this presentation.
Okay.
All right. So for the additive structure in GP, so the most like common one is generalized additive kernel called GAM. So where they kind of have like, so they put like all the dimensions into a kernel, and they have the number of subkernel is equal to the number of dimensions of the true input, like input space. So for example, like if I have a function of x1 and x2 and x3, so is if it follows the structures of fx1 plus fx2 plus fx3, then it follows the GM structure. So it means like we cannot have any coupling between any variables. So there's no the idea of grouping. So the issue with this is the model assumption is too strong. Normally, like for example, if you have a term of x1 times x2, the GM will fail. And the second approach is we learn a decomposition. So where we introduce the idea of the group. So we are not, so for example, if the same function of fx1, x2, and x3, but this time if we put x1 and x2 in a group, so we can allow the term of x1 times x2. So the problem for this is as the dimensional like input space become quite large, the decomposition, the number of possible decomposition goes like out of one. So finding the good decomposition, learning the good decomposition is hard.
So how they I have a question. So how they learn the groups, like for the sec for x1 x2 is the group and x3 is a group.
So actually like we're gonna discuss this later. So
Okay.
So for short is like they use a GP marginal likelihood and so they learn like for every possible decomposition they learn a GP and they test the GP marginal likelihood and select the higher one, the one with higher GP likelihood. So that's why it's
so they enumerate
exactly
enumerate all the groups. Okay.
Exactly. So that's why it is impossible to learn like a good decomposition.
I see. Okay.
Okay, so for the third point is like third approach is to, because like we know GM is too strong of a assumption and we know learning decomposition is hard. So why not we just learn like do the projections and we learn the projection matrix. So the projection pursuit is like to learn the eta j and the number of kernels equal to the number of projections and we add them together. So the problem with this is like learning the projection by sampling is slow and hard. And if we treat the projection matrix or like projection vector as parameters, then we use the gradient method to optimize this, it will overfit because we are introducing new parameters. So the paper one that we're gonna discuss today actually use the random projection. So they don't like learn the projection because we know like why we will overfit because we introduce the new parameters. So we just don't use any parameter. We just sample the projection matrix from let's say a Gaussian distribution. So the issue with this, like what I found is like we often need like mining like a large number of random projections for like low like kind of like the input dimensions below 500. We need a lot, like kind of similar to the original input. And this is also sensitive to the choice of the number of choice of J. J is the number of total projections.
Hi, Zitong. I'm Sui. I have a little question. What's the relationship between the F prime and F double prime and F triple prime?
Oh, they just indicate that we don't have those, doesn't have to be the same like function.
So they are independent function. They don't have any relationship.
Yeah, they don't have any relationship. You can view it as FGH or whatever.
Yeah.
You can view it as a so the generalized additive model essentially assume a structure that your function of 3 variables is the addition or sum of 3 functions, where each function is only applying to one single variable.
Okay, so it's like they decompose the kernel function in this form.
Yeah, if you decompose the kernel function in this additive form, like kx, remember x here, and this prime here is a vector. So if you assume that, okay, my kernel is a summation of the kernel functions over each individual elements of x and x prime, then it is equivalent to assuming that, okay, I have a independent GP prior over functions of x1, function of x2, function of 3, and then add them together to get f.
Okay, thank you.
Thanks, Professor. Okay, so the method is actually really simple. So the kernel, like for the random projection, is actually like we sum all the kernels with the projections, and the alpha here is the auto scale. So this is always set to 1 over j, and j is the total number of the projection. So only one thing we need to pay attention is like the weight of the projection matrix or projection vector. If they are going to the one dimensional case, it needs to be centered from an isotropic distribution. So zero centered normal will work. We will see why this is the case. Okay, so for the propositions, like
I have a question about the previous
Yeah.
slide. So why they scale sample the normal distribution with the standard deviation 1 over dj, not just 1.
oh, I think you can samples for base 1, like the variance is
Okay, so this is more like a numerical trick
yeah.
for,
So I
for,
think when you
for
rank
stability. Okay.
yeah, for stability.
So how's
So-
the choice of J?
Huh?
Zhitong, what's the practical choice of J? Can you go back one slide before?
So they didn't like actually provide the so J is fixed as long as they start the Gaussian process. So normally, like I think, like for me, like I test their code, like if the embedding is really, so actually, like I can show you the result. So what they did is they increase the number of projections. They do this kind of experiment.
Okay.
So
So
J,
yeah, Zhitong, one thing. So
Yeah.
you mean so first your projection
Mhm.
like this PJ times X will give just one dimensional? One dimensional, just give a scalar?
no, it will get the DJ dimensional.
DJ dimensional. Okay.
If
And then
yeah,
your figure in page 13, I guess. Yeah. Your figure, what's your choice of DJ?
the DJ is 1. So they so in their paper they always treat DJ as 1. So they think as they say it's they produce like better result empirically. So I think like if they like, because they are all sampled from a normal distribution, like if DJ is 2, it's kind of like having two like one dimensional projection vector, then concatenate them together.
Then if you pick up DJ as 1, so basically it means that, okay, you do the random projection, you get one scalar, and you do another random projection, you get another scalar, and then
Yeah.
you do the additive structure over those over this
Exactly.
projected features, right?
Yeah, exactly.
And then can go back to slide 13.
Yeah.
So what's
This-
the okay? So the RBF ARD, the blue line is just you don't do anything, just apply ARD RBF kernel.
Yeah.
Yeah, you see that actually the GP field here, it doesn't learn anything. But if you do the random projection and then add them together, it performs much better.
Yeah, and also like the general GM also performs surprisingly good. They also note in their paper.
What's the red? What's the red?
Oh,
What-
red is like so the green line is like if we diversify all those projections, and red line is just random. So R stands for random and D stands for diversify. It's a trick that we're gonna cover.
Okay, so the red one is just random projection.
Yeah.
And
It's a diversified projection.
Okay, so the orange one, general additive model.
Yeah, it's yeah. So it's
It looks like you're doing random projection, and then add them together is still worse than general additive model.
exactly. So they also got like, I think they also what they wrote in their paper is like GEM got like surprisingly well. I mean, the dimension is like 1,000 and like almost 2,000.
This is the surrogate performance, right?
Yes.
Okay. Yeah, it's surprising because GM assume those functions are non-overlapping, right?
Exactly, and this data set is on image. I think like I read it's kind of like they take the image and they transform that.
But when you add some diversified technique, then perform random projection, it kind of like beat the general additive models greatly.
Yeah.
Okay, that's interesting. Yeah, continue. Please continue.
All right. So I think the proposition one is the most important, like for in this paper. So what is trying to say is like, suppose like, okay, so this is for the 1D projection. So the DJ is 1. So I think they just want to make the things easier. And also the 1D result is good empirically. So suppose like we have a phi function that is a low dimensional kernel that transform like a real number to negative 1 and 1. So that's first requirement. And if our eta j, the projection matrix, is sampled from a isotropic distribution, then as we increase the number of j, we're gonna have an expected kernel. So if expected kernel is a kernel that operating on the L2 distance. So I think they didn't write it clear. So it means like, so it fixed the first point as origin. So because kernel takes 2, so they fix the first point as origin. Okay. So I think this actually makes sense because like, so for RBF kernel, it work on the distance. So it's gonna decay. So the covariance is gonna decay along every direction with the same rate. And by the nature of additive kernel, this is a GEM kernel. So it's gonna decay along this axis and along this axis. So if I add them together, so they're gonna have like they're gonna like decay really fast, like if they are not following the 2 axes. So what they are trying to say is like, if the number of projections increase, we're gonna have a kernel that almost like spherical as so it's gonna converge to a spherical kernel. So this is the third plot is a random projection with 16 projection, with 16 projections and but random. So you can see it's almost getting there, but like not quite. And the first plot is also with 16 projections but diversified them. So they try to maximize their like separation degrees.
So they're saying that they're claiming that this expected kernel, I mean the spherical kernel is better.
Not quite. So because like what they want to do is they want to use this kind of approach, additive kernel, in even like additive black box function. So for the second one, like it's the GEM like this one, it will not work really well in the non-additive function. Yeah. So but with like a lot of number like projections, they will have this kind of like. We will have like, so they will have the advantage from like additive structure, and they will also can model on the non-additive function. So they have 2 advantage. I think what they are trying to say is this.
Yeah, the problem here is that if we want to do this expected kernel, you can just use RBF, right? Yeah,
but like, so it's kind of like for a function like, let's say a cosine function, we can decompose, use the Taylor expansion, but they are same, but like the reason why we do the Taylor extension is because we want to have some other property. So this, why they do this is they want to have the additive property because this is low dimensions kernel. It's easier to learn. It will not fail in the Gaussian. So it will not fail in the GP process.
So I mean they use many random projections to approximate the original Gaussian kernel or RBF kernel.
Yeah, I think we can. Yeah.
Yeah, but I'm not convinced that there's spherical. This is just the the expected kernel essentially is just the stationary kernel.
Yeah, it's a stationary.
The stationary. They want to they're just saying, okay, if you do enough number of random projections, you're gonna recover the stationary kernel. That's it.
Yeah. Yeah.
But the problem is that it's really worth doing a stationary kernel.
So I think so if we think about this example, for example, like this one, this is kernel will not learn the decomposition.
Yeah, of course. You can always construct such kind of examples.
Yeah, so I think what they do is kind of like this. So I think what they do is they just want to. So actually, I also found in low dimensions, dimensions below 200, they need almost identity, almost 200 number of projections for a good RMSE for testing. But as a really high dimension case, they don't need so much. We only maybe need 200, and that's it.
200 projections?
Yeah, 200 projections.
Okay. Yeah, I think that proposition might reveal the connection between the additive kernel, the random projection, and common use the stationary kernel. But the fact is that people, if you can construct a non-stationary kernel, people will usually be in favor of that rather than going back to the stationary kernel.
Yeah.
Yeah, but go ahead. This is just showing the connection.
All right. So some colors. So I think those colors are pretty interesting. I read through their proof and I think they are really interesting. So if the low dimensional kernel is let's say RBF, and eta is sampled from a normal distribution, we're gonna have the expected kernel is gonna be the inverse multi-quadratic kernel, and it's operating on the L2 distance. And if they choose the low dimensional kernel to be cosine function, and eta also sampled from zero mean Gaussian, we're gonna have the RBF.
Oh, so what is phi x? It's a kernel.
Phi x is just this low dimensional kernel. It can be a function or a kernel.
Oh, so this is a low dimensional kernel. It's also a stationary kernel. So it's okay. That's why it's you only have the one single input. Okay.
Okay, so that's all the method, and they going for the tricks.
Okay.
So the first trick is maximize separation. I think this is really similar to the trick we use in support vector machine. So the goal is previously we know we're gonna have we know if J is going to infinity, we're gonna have the convergence between this one and this one, right? But in practice, we cannot have infinite number of projections. So
another thing, Zhitong. So now that they can prove in a limit what's the form of the expected kernel, why not they just use that expected kernel to do the inference? It's still not working.
So I think it's because the expected kernel is not going to work on the high dimension setting.
So you directly use the expected kernel, it won't work.
Yeah, so it's not going to work because it takes distance. So it's kind of like we are not going to take the low dimensional kernel as sum of them, and then to approximate this.
Okay.
So what they are trying to do is like, so J is not going to infinity, like for sure. So J is a fixed number. So how can we make the most out of those J projections? So what they do is like they define the separation, and separation is kind of like from here, the separation is like the minimum, the angle of the closest two projections. And we are trying to maximize the separation.
So
And we are
eta j is each eta j is a vector.
yeah, it's a vector. Yeah, here it's a vector.
Oh, it's the minimum of the it's actually, so they use cosine, distance, right?
Yeah.
Then this actual cosine inverse is essentially the angle,
Yeah, the angle.
and they define the separation as the minimum pairwise angle between those projections.
Yeah.
Okay.
Yeah, I think this is similar to the definition of the margin in the SVM. And we cannot directly maximize this. So what they do is like, okay, so let's define a loss function. And so we are trying to minimize the loss function. And note here is the power of 4. So why the power of 4? I read through their code. They said they want to make the sign invariant and also differentiable. So they take the power of 4. I think power of 2 gonna do the job. I don't know why they took the power of 4.
So why do they minimize this?
Oh, because I think it's
To maximize the angle. Okay. They want to maximize the angle. Yeah, the larger the angle, the smaller the cosine value, right?
so I think the larger the
Or the dot product. Dot product represents kind of distance.
distance.
Okay, the smaller the dot product, the larger the distance. Oh, okay. Then that makes sense. Okay.
So yeah, so they just do this kind of trick.
Yeah, if they can, in the ideal case, if this summation is simple to 0, mean that all the projection vectors are orthogonal.
Yeah.
Okay.
So the second trick is easier. It's just adding the ARD, the automatic relevance determinant. So the only question is, where should we add the ARD, before the projections or after the projection? So put A inside P and X or outside P and X. So they say like it's gonna, from empirically, I do the ARD before the projection gonna have better result. So they have this form.
What is A?
Yeah.
A is a diagonal, like S in Lancio.
Oh, okay. So A is a diagonal matrix.
Yeah, it's a diagonal.
PJ are still like random numbers.
No, P is always random number. But so P is after the trig 1 is not that random anymore.
Yeah, I guess PJ here correspond to etas in your previous.
Yeah, exactly. Yeah.
And they want to just solve the optimization problem to determine a sequence of etas. Okay?
Yes.
And here you pre-generated a bunch of PJs.
Yeah.
And then you just learn the kernel parameters A. That those are just length scales.
Yeah. So A we can have we can have gradient back to A.
But what's the reason you want to? This is like feature selection, right? If you do the, it means you're gonna prune from attributes in X in every KJ, right? So what's the rationality? It seems has nothing to do with orthogonality.
So they don't have any reason. They just say like it works empirically better than having a after the projection.
Okay. Yeah, we know that SUSBO is also doing similar thing, right? The
Yeah,
difference is that they're not using ARD, they just put additional prior over
yeah.
X. Right?
So I think the main idea for this paper is like learning decomposition is hard and learning the projection will overfit. And so why not just use a random projection instead?
Is the first paper?
Oh yeah,
Which-
this is the first paper.
Which paper? Was the 2018 paper?
This one, yeah.
Okay, that paper proposes two ideas or just proposes the ARD?
Oh, one idea. This one is like my summary. Oh, sorry. So this is my summary. Like,
Okay, so what's the contribution of that first paper?
so I think the first paper is like the contribution of first paper is like so what they did is so they make the previous like learned projection into random projections, and they also yeah, that's the only contribution.
So their learned projection is by maximizing the dot product or minimizing dot product distance, or by introducing the ARD.
Oh, there are two kind of tricks. So you see like so the DPA, D stands for the diversify. The RPA is like we are not going to add the diversify. So if there's a DPA, so it means like they are using the trick 1, and if there's ARD, so it means they are using the trick 2. So
they propose the both tricks.
yeah, so they propose both tricks.
Okay.
Hi, Jidong, can I see the proposition 2 again? The
yeah,
proposition 2 is
Proposition 2 is like kind of like it's kind of just saying like they bound the convergence rate.
yeah. So basically, so on the right hand side of the slide, so they want the random projection more spread instead of.
No. So I think like this doesn't like do anything for like this doesn't give the intuition about the
No, I'm asking the right hand side of the. So what's the objective? To minimize the power 4.
oh
So they want to make the random projections more spread instead of. So they want to convert the diversity of the random projection.
yeah, so they want to make them like more diverse for the direction.
So is there any way that we can so for example, we sample eta1 from a normal distribution, then we can sample eta2 that is orthogonal to eta1. Is it possible?
Yeah, but the thing is like so for the case like what if you have more projections than the actual dimensions? So we don't have so many orthogonal bases.
Okay. Let me. I was thinking. I would remember there's something that we can sample a series of random projection that is orthogonal to each other. Okay, now mind.
I see.
Yeah, I'm thinking of one thing, like why not we just we just use Gram-Schmidt to do this, right?
Yeah. The Gram-Schmidt.
Like you just generate a random matrix, right? So each projection
Yeah.
matrix is one column of random projection matrix. Then you apply a Gram-Schmidt.
Yeah, Gram-Schmidt.
This is orthogonal to each other.
Yeah.
Have you taken a look at how they minimize this summation of
They just throw into either.
oh really?
Yes.
Yeah, yeah, I think it's really stupid. Yeah.
Yeah. So I checked the code. They just throw this into either.
Okay, yeah, maybe Zhitong, think about that. Like, we can do Gram-Schmidt, and then you can imagine like right now, because each eta is actually vector, right? You can consider we are trying to project the inputs into a set of bases.
Yeah.
And that means the projected space are kind of like orthogonal to each other, and then you can view as like different tensor modes, right? Because we can naturally we'll think of we will like, okay, different tensor modes should be orthogonal to each other.
Mhm.
Yeah, we can talk about that offline.
Got it. Thank you, Professor. So yeah, I think like this experiment shows like, okay, so for the dataset concrete, autos, and housing, they are like realistic dataset. So I don't think they are like, so they are probably not the additive structure because they are realistic dataset. And we see like, so as the number of projections increase, they have like they are converging to the stationary kernel, and they are like on really low dimensions. And the one with the trick 1 and trick 2 works the best, the purple line.
Pick one is the red line.
Sorry.
Which one is the trick one? Is DPA the red one?
So the green line is the one with no trick. The red line is the one with diversified trick.
Okay.
And the purple line is with all trick.
Purple line is the ARD trick, or
With ARD and diversified. So they do two.
oh really?
Yeah.
That's weird, right? If you got like orthogonal projection, why do you learn the land skill? Oh, but anyway, yeah, it's natural to learn additional kernel parameters. But that's but there are also many, right? If you have very high dimensional data, like you got 100 inputs, like for each projection you're gonna have 100 length scales, right?
For each dimension they have yeah.
Or they're all they share the length scales.
Yeah, so for each dimension they're gonna have a length scale. So if the input space is 100 dimension, they have 100 depth. So the A is 100 times 100 like
okay. A is shared by all the projections.
Oh yeah.
Oh, okay. Yeah, that's not too bad. Okay.
Oh, sorry about that. I didn't make it clear. Okay, so this one shows like they are converging as the number of projections increase. So this one shows like on like really high dimensions, like the one with trick 1, trick 2 gonna work really good, and the stationary kernel like RBF kernel is not going to learn anything, and GAM actually perform really good. Like they also say it's perform like surprisingly good.
Oh, so the green one is the orthogonal. They're trying to maximize the orthogonality of the projections.
Yeah.
Projection vectors, and also add ARD.
Yeah.
Kernel. Okay.
Yeah.
And
so the red curve doesn't work because the projection weights are not orthogonal enough, right? So this is their contribution.
The red one is just a random projection with
because with not the diversity.
Just random projection.
Yeah, just a random projection without any trick. You just a sample from a normal distribution. It doesn't work because the sampled width are not orthogonal enough.
Oh, okay.
Yeah. So if we use true orthogonal random projections, it could be surpass the green line potentially. Because for the green line, the diversity trick, you cannot make sure that they are orthogonal. You cannot just maximize the separation. Doesn't mean it's orthogonal.
Yeah, I think that is worth trying. Yeah.
Yes. So I think Grashmeet is you can try Grashmeet maybe.
And Judo, you haven't tested like just using diversify without ARD kernel.
I testified. No, I didn't test. I actually testified with their code without ARD, so it doesn't work really good. So I tested on the I think Rosenbrock and the Steptown, and it doesn't work really good.
So you have to use the ARD kernel.
Yeah.
Oh, okay. So
And
you have to learn a different lens skill for every input.
Yeah.
Okay.
Okay, so I think that's probably all for this paper.
Yeah.
So we can move to the background on additive model with decomposition. So this kind of approach is like we are going to learn the hardware. We are going to learn the decomposition. So the first paper, those three papers are like really well known and they are like really closely connected to each other. So the first paper is like, so they propose a additive model for Bayesian optimization, and they learn the decomposition by maximize the Gaussian process marginal likelihood. And this doesn't work really well. It can be work really poorly because they only randomly select certain decomposition out of all those possible decomposition for every n step in the BO loop. So it works really well.
What do you mean by random select the OD composition?
So they just out of random. So it was it was a randomized algorithm. So they just trying to draw the dice.
I mean, from the text you posted here, it proposed additive models for BO, right?
Yeah.
That means it assumes that the GP has the additive structure in the kernel.
Yeah.
And then they use say Thompson sampling or EI to perform BO. Is that true?
They use UCD. They use this is the paper.
Okay.
Yeah. So but the thing is as I think I put it here. So we're gonna learn the decomposition. So the grouping.
Yeah, I mean,
for each group, I think for the 2015 paper, they just for each group they just randomly sample a subset of the inputs.
Okay,
yeah.
Okay. So they do this every step, or they just do it
every
once?
n step of the BO loop. So they fix the decomposition and they generate the BO loop n step for n samples, and then they learn again.
So they then they random partition again.
Yeah.
For variables, and then
Yes.
use additive structure.
Yeah. So basically, let's say they select 5 decomposition, and they learn the decomposition and they compare which one has a higher GP marginal likelihood, and they decide the highest one is a true decomposition, and they continue for another n step, and then they do this again, and then they yeah.
Okay.
So it works really well, and I think they also acknowledge that in the paper.
It doesn't work.
No, it doesn't work in real data set. So I think what they say is if we know the function decomposition, we're gonna perform really good. But I mean the idea for the Bayesian optimization is a black box optimization. So we shouldn't know the decomposition.
Yeah.
So the 2018 paper is kind of built on that paper. So it was assumed the decomposition graph can be potentially fully connected graph. So they treat like every input dimension as a node. So there is a potential edge connecting them.
Mhm.
So we only need to learn the edge parameters. That is only like d times like d minus 1 divided by 2 because they are undirected graph. And we can do this by Gibbs sampling.
Okay.
They also allow for, because they are like a connected graph, so they also allow for the overlapping groups. And they introduce the way of the message passing. So they need to, for every click, so we need to have a kind of like root click, and we do the message passing to the root click.
Oh, so okay, they build up a graphic model
Yeah, exactly. Junction tree.
and then enumerate the maximum clicks on the graph to form the groups.
Yeah.
Each group corresponds to a maximum click in that graph.
Exactly.
Okay.
So the third paper is, I think it's like, it's almost identical to the second paper. So the first author, so Roland is actually like the last author for this paper.
Okay.
So it was almost identical to the first paper, but with it assumed the decomposition to be a strict tree structure for easier like message passing.
How do they model the graph, the graphic model?
Just like, so they treat every input dimension as a node. So we're gonna have a dependency graph.
Yeah, so they are assuming is fully connected, or how do you choose the graph structure?
So it's by learning the edge parameters.
So what's their potential function on the
No, they don't do that. So they don't do that way. They just use the junction tree to do the message passing. It's kind of like only to make the computation easier. So for the overlapping groups, we are not going to optimize them twice. So
I mean, if you run junction tree, that's fine. I mean, but you have to define a model on the graph, right? So you're assuming that they are a priori is a fully connected graph, right? And then, if you want to learn the graph structure, you have to assume the parameters are sparse.
I think they use Gibbs sampling like for the edge parameters. So they place a prior, I think, like as for every, so for those kind of parameters. And like they just use the kind of like Gibbs sampling, they know the equations in there. And so I was also got confused by the junction tree. So they didn't go through the psi function. So I think like the reason why they put the junction tree in this is only to make the paper easier to understand, because they use the whole idea of the message passing as it's kind of weird. Like,
Yeah, I understand, but you need to know how they define their graphic model. Junction tree is a classical algorithm. We don't need to care about that. But the problem is how do you define a model? Like if you, for example, if you define, so this is x1, this is x2, this is x3, right? So suppose you got such a model. You need to define the potential function, either on pointwise or
they didn't
wise.
So they didn't do that. So I think what their junction tree is not like the one in the graphic model junction tree. So they only use this to, I think, to make this idea easier to explain. So it is not a graphic model. So the group is not doing like, So I actually also got confused by that point. I think so. What makes like so fun, like in the end, like what I think is like there's nothing with the psi function or the potential function. It's only to make the algorithm like easier to work.
Okay, there must be some definition on that. Otherwise, how do you get the structure?
Right? They don't like, they didn't put connect this with the graphic model. I think like I can show that paper right now. So what they do is like, I think in this algorithm, like just this only for the it's more like a graph, like traditional graph algorithm, like but just like easier to for us to understand. That's why they bring up the, so it's nothing related to the like the probabilistic graphic model.
So what is 5C?
5C is the function, the kernel function. The one they are, it's the acquisition function that we're trying to maximize.
I think there seems like their potential function is defined by the acquisition function.
But how do they compute the acquisition function?
Equation 5. Can I go to equation 5?
Yep.
For each node, they compute the
Okay, UCB.
UCB, yeah.
Okay. So
And
okay,
they use
so
message passing.
FI
compute
is
the-
a GP learned on XI.
You mean the phi?
Yeah, phi TI. This is UCB. This is UCB, and the global acquisition function is sum of low dimensional nodes. 6. Yeah, that's reasonable. How do they specify the? How do they specify the?
Oh, this function.
Yeah, this is UCB, right?
Yeah, this is just from the GP.
Yeah,
So
and
it is a GP. So I will click. So 1, 2, 3 they form a GP, and 1, 3, 4 they form a GP.
So given the GP of 1, 2, 3, 4, so can you compute the marginal distribution of 1, right?
So
Because the equation 5, I think the acquisition function is defined on the node, not the clicks.
I feel like I think that's a click. So let me
That's
go
a
through.
click, okay, yeah,
So
okay.
let me go through into detail. So let's ignore the PON6. So
Okay.
so we have like 3 groups from 1, 2, 3, 5. 1, 2, 3, 4, 5. We have 1, 2, 3 is a click, and 1, 3, 4 is a click, and 4,
Okay.
5 is a click, right?
Okay.
So let's define the 1, 3, 4 is a root click. So if we don't do the message passing, then we have like
Yeah, it's defined on the click. Sorry, yeah, I saw that.
so for because we have message passing, so for the first time we are maximize this one, we only maximize the 2, and we put like 1, 3 as in function for, and it pass into the next click. And for the click of 4, 5, we only maximize 5. With the result, we maximize the value for the root click is 1, 2, 3, and we maximize this.
So
Yeah.
you're saying that their dependency graph structure is given.
Yeah.
They're
Look,
using junction tree to maximize the whole acquisition function.
Oh, sorry.
In the second part, they can learn in the second part of this paper, they can learn the graph. But in the first part, they just assume that you have a prefixed structure.
Okay, so if you have an overlapping graph structure, you can use junction tree to efficiently maximize the whole acquisition function. That's okay. But how do they learn the structure?
Oh, the structure they use the give somebody. So they place a prior definition and they use the give something for if this is equal to 1, then it means there is a if this is they define the probability of this. So Zij means like the edge of node I to node Z, node J.
So to learn the structure, they assume they start from the fully connected graph, right? They just want to estimate the pairwise edge indicator Zij, right?
Yeah, I think so, because like I didn't find their code, they didn't, so I only read from their paper. I think that what they are saying. Yeah.
What is their observation DN?
Sorry.
What's DN here?
The
How do they define DN?
DN I think is I think the DN is
Oh, likelihood.
oh
Okay. Can you go back to one page before?
Okay.
Okay, learning dependency graph. Okay. So their DN is this one. Oh, I see. Okay. Okay, it's very tedious procedure. Okay. Yeah, so they define the likelihood. Well, your Z decides the graph structure, right?
yeah,
And
exactly.
the graph structure decides the kernel decomposition form.
Yeah.
And then you use give something to do that.
Yes.
Oh, okay.
So it's pretty tedious.
Oh, I see. Okay. Is this working?
So they didn't publish the code, but according to the result, it's working pretty good. It's working pretty good, better than non-overlapping and like yeah.
Okay.
So yeah, so I think I discussed this with Shibu like last time, and yeah. So I think actually this one is better than the third paper. The second paper is better than the third paper.
Well, how about this third one? Third one, is it also like learning a tree structure?
Yeah, it's almost identical, but right now they only focus on a strictly tree structure.
How do you restrict your sampling of these to form a tree structure?
I think it's like if they so I think like I kind of forgot, but I think it's like if they have if they have two edge, and if the next edge is gonna to make a cycle, they will consider it as a
Okay, they just do the rejection.
yeah, they just do the reaction. Yeah.
Oh, okay.
So yeah, so I think the second one is a best among them all, and yeah, this is only for like easier for the learning part.
Yeah, I'm not sure whether it's useful to use junction tree. Why not? Because they got the additive, they got the acquisition function, right? They just calculate the gradient, use the automatic differentiation. That's it, right?
Oh, I understand. So I understand what I'm saying. So the thing is like, I think what they want to do is like, so if this idea starts from the first one, so they want to do the kind of like parallel, like so they want to make it faster. So that's why they use the junction tree. So
Okay.
so they build from the IGP UCB. So I feel like sorry about that. I didn't include much detail of this three paper. So what they want to do is kind of like, so from the first paper, so they want to maximize them like separately. So they want to make them like maximize, because like if they are not like overlapping, so we can maximize like each group separately. So if they have a parallel machine, we can do them like parallel.
Okay.
Yeah, so I think they are building on this idea. Yeah.
Yeah, but junction tree, while you do the triangulation, you're still doing the message passing from the bottom to the up.
Exactly.
Well, I mean, it can do parallel, but I'm kind of skeptical. What is the gains of the speed?
Yeah. So I was also
you can save the computation in some sense, but against modern computer, like you are just optimizing a function with 100 inputs. That's not a big deal.
yeah. So I was also so really confused about their junction tree. Yeah.
Except this can add to some complexity to our method. I don't see too much benefit on that. I think the most valuable part is how do you learn dependency graph?
Exactly. Yeah.
You skip something. Yeah, that's interesting, but I think that's not That's also quite costly.
Yeah.
And also this give sampling. Oh, one thing is this give sampling. Can they do give sampling on that?
Oh, actually, so I didn't go through their I didn't double check their derivation. So I think if they can have this, then we can do the give something. Like if
That's their give something update, right?
yeah, that's the give something.
But every time they can just update one edge variable, right? ZIG.
Yes. Yes.
Yeah.
Then it still be very, very costly, right?
Yeah.
Yes.
Oh, you got 100 variables, like you got
So
10,000 edges.
10,000.
so none of those three papers publish their code.
Okay.
Yeah, if you do give something, like if you're using you're going through one iteration, how much cost, how much time it will cost, right? It's very expensive.
Yeah.
But they can argue give something can update parallelly.
And also this is almost like D square number of parameters. So for example, we have 100 dimensions, we have almost 10,000 parameters for give something.
Yeah, that's just the one for one iteration of give something.
Yeah.
Give something cannot, I mean, in this case, at least in this case, it won't be done in parallel because you're going to
Okay.
start from the fully connected graph. It's
Okay. Oh yeah. Okay.
Yeah. So
yeah, but anyway, it's interesting. I'm just curious, like how they weren't any reviewers questioning, is this really useful? It's not useful at all in practice, right?
to be honest, I don't know what is the purpose of the third paper. I have no idea. Okay, so
But if they have some smart design, like you don't need to do the rejection and keep something, that's good. But if it's just the rejection, right? Just check if your samples contains loops. Then you just reject it. It will be even more inefficient than the second paper.
yeah, so
Okay. Yeah, go on. Yeah.
so what they claim in the second paper is so recall that we learn decomposition from data, and what if the data we already have is misleading? So especially for the Bayesian optimization setting, the data is limited. So now they give this example. So if we are going to learn the tree structure, we will never decompose the actual object. But if we use a random UCB, and we're gonna discover this. So here's the algorithm. It's only
Which paper is for this algorithm?
this one is 2023 SAML.
Oh, okay. This year's essay. Okay. They're talking about the problem of
So
okay.
what they do is instead of learning the decomposition, they just sample a tree, and this is completely random.
Okay.
And but actually they got a really good result. This is a 250-degree dimension step down, and they got sudden drop with their random UCB.
How do they randomly generate the tree structure?
Oh, I checked their algorithm. It's kind of so I'm not quite sure, but they just randomly set the edge.
Can you say it
So-
again?
So I'm not quite sure about this. So they put the random generating tree algorithm in the supplementary material. So it's only is there an edge? So that's random. So I see.
Or if it forms a loop, it just delete it.
There's just randomization. So there's not learning. There's no learning from data. So yeah, it's kind of that's idea. Yeah, if there is a loop, that's deleted, and they are not going to form the loop. So I think the idea is really simple. It's like this. There's no learning happening. Just general tree, like with all the nodes, we go get a tree structure. They do so when I see like they are doing like a random permutation of L, I know like this is gonna be completely random.
They sample the node or sample the edge?
Edge, I think it's edge.
Okay.
Because node is already defined.
Oh, I
No,
see, I see. Yeah, it's just to do the random permutation
Yeah,
and then random and just connecting them.
Yeah.
Okay.
And if there's a loop,
so yeah.
so once they create a tree, they still pick up the maximum click to form.
No, there's no learning. Like there's no learning in this paper. There's no learning. It's completely random. The tree structure. They don't do any learning.
But once you get this tree decomposition, like in line 4, right? And how do they partition the variable groups?
Oh, I think it's similar to this one.
But if it's just a tree, that means each group will be at most the size 2, right?
They didn't give.
Yeah, you can only include one edge into every group, right?
Yes. They didn't show the like detail, but like they have like a heavy citation of this paper. So
Oh, this 2021 paper, they got a tree structure additive model. That means they restrict group size to be 2.
yeah.
Okay.
So yeah, so this paper only shows like by doing like those randomness and not learning completely from data,
Mhm.
they will have like better result.
But why is this better than random projection?
So this is actually the discussion question I want to ask. Like I think like by doing random like decomposition and random projection like in the first paper, they should have like they can solve this problem like equally well.
Yeah, you are considering overlapping as well, right? Overlap as well.
Yeah.
In the random
Yeah,
projection.
so this one and this one are solving the same problem but in different approach.
But looks like if you just do the random projection multiple times, it works much worse than the other methods.
So Rumble is really bad. Rumble is really bad. And Alibo, I remember, it's also not great.
Rambo here, does it learn phi as well, or
No, Rumble is completely random.
so just to do the random projection and add them together?
So this was a really old paper. Like I just like went a skim through, and this paper I also read this paper. So this is I think this is kind of like re-examining the Rumble. So Rumble the model after learning is really bad. So we can see like it's really bad.
Yeah, for the ICML 23 paper, the newest paper. Yeah, it's hard to believe that if you just completely random generate the tree.
Yeah, that
So how
was my question.
How is it possible? I mean, what's the rationale? It can outperforms completely random projections.
So I think what they say is like if there is like a random like by the random decomposition, like if we got 1 point in here,
Huh?
and then they're gonna have a better data, and then the other randomness will have like better and better result. So the thing is like I'm quite like shocked is like because they are doing the randomness like every loop. So decomposition, I think it's gonna be really bad, to be honest.
So,
And I think-
okay, so every time they just randomly generate one tree, right?
Yes.
And then they do the decomposition according to the tree structure, fit GP, maximize the UCB.
Yeah.
And then they add the new data points, and then they do the random something again.
Yeah.
Is random projection? I mean, for the random projection method, do they perform the random projection just once, or they also do random projection at every step?
Oh, you mean the first paper?
Yeah.
They only do it once.
Yeah,
Once is
they're kind of skeptical, like if they are choosing, this is because the scheduling of the experiment. Did you test their method by yourself, or you just look at the result?
the second one.
I mean, this one, this random tree generation approach.
No, so none of those papers like published their code, and this one didn't publish their code as well. I think like I will keep an eye on their like paper. So probably like after they got yeah, so they already got like selected. So maybe they will publish their report.
Okay. Yeah, very interesting. So do you have a more slides?
Oh no, that's it. So here is a reference, and here are some like their talk by the original first author. Yeah. And this one is the one, yeah. So that's it.
Yeah, yeah. If I were the author of the random projection, I'm gonna ask him, what's your do they provide any theoretical analysis?
Oh, their theoretical, they do, like their theoretical analysis is more drama. It's like, so I think what they say in their theoretical analysis is like, we are going to do the random search, and we are going to limit our search with only certain structure. I don't think this is have any contribution to our like to the follow reader. So I think like when I read it, is like their theoretical is like I don't quite understand. I don't think there's any useful like for our like purpose. They do have like I also listen to their talk there. I'm not quite convinced by their theoretical, because everything is that they define by themselves. And like, so yeah. So I think like their point is like, we want to have randomness first, and we want to do the randomness search with only a certain structure. So they choose the tree structure, and they didn't say what.
And what does this what do this theorem tell us?
Just search within the tree structure, a limited set. That's it. So don't consider the like other kind of the structure, like the fully connected potentially, just searching the tree. I think it is impossible to search in the fully connected structure. So they choose the tree structure. I don't quite understand their like theoretical guarantee, to be honest.
Okay, the maximum information gain for a square exponential kernel following the decomposition only with pairwise components in d dimensions upper bounded by. Okay, so when it comes to tree structure, which we now proceed to define. Okay, so the proposition 4.3 just means that, just saying that, okay, it's not saying anything, right? It's just
Yeah, it's not saying anything, so I didn't include any of their like
because you
any
should,
of their theorem.
What do they mean by? Yeah, that's proposition 4.5 is very natural, right?
Yeah, so
And won't give you more information than you consider all pairwise interaction.
exactly. So I didn't include any theorem in this paper for this paper. So only like the result and the idea. So yeah.
Okay.
I don't think it's useful for us, to be honest. Yeah. I think that's it for this presentation.
Okay, yeah, thanks, Zhitong.
Thanks.
Very good, yeah. I think we should talk, we should think about that. Because right now in low dimensional space, like you tested on Stylish Tang, right? You tested on Rosen block.
Yeah.
Our tensor train decomposition seems much better than standard GP.
Yeah.
But for the standard GPU tested is also with ARD kernel or not?
Oh, with ARD kernel.
Okay. Yeah, and then yeah, we should use some diversified technique to find a set of like orthogonal projections, and then consider, yeah, maybe you can just consider random projection with one dimensional, right?
Mhm.
So
I actually put their code, like I actually added, but so it doesn't like do much improvement. Like sometimes it's even got worse than our like original TTE result.
with how many dimensions have you tested?
So I tested on the dimensions of 20 for Rosenblock, and yeah, and I use like 20 projections. Like so anything below 20 is not going to work. Yeah.
Oh.
So so right now I'm writing like to put, because like we update our land scale in HMC. So I'm thinking like how to update the land scale with gradient method.
Yeah, you may think about, okay, when so the diversified trick is from another paper, right?
Yeah, it's from another paper.
Yeah, so yeah, you might need to consider adding the ARD kernel.
Got it.
It looks that is very important.
Yeah, that's exactly, yeah. So ARD is really performing the best.
Okay. Yeah, thanks, Zhitong.
Yeah, no problem.
Yeah, I think yeah, can you stop sharing? So I think next Keyan will present something about hypergraph neural network learning.
Yeah, sure. Let me share my screen.
Yeah, Keyan, I have to break your presentation into two parts. One part will be about 30 minutes.
Yeah, no
we start
problem.
at 11:40, and then we return at 12:30 or 40. Yeah, and we continue until 1:30. Yeah, please go ahead. Sharing your slides.
So, can you see?
Yeah.
Okay. So here the first one. The first paper is about the HyperGCN and the new method to train the graph convolutional network on hypergraph. So first I will introduce the outline. It includes the hypergraph introduction and the GCN background and the paper's contributions. The hypergraph introduction is about, we can say the hypergraph is provide a flexible modeling tool to model a complex and go beyond the pairwise relationship. The examples are the co-authors and the email communications. The co-author is also the data set that the paper do some experiments on it. And usually the simple graph is that we define two vertices to construct the common graph, and the hypergraph is to contain the multiple vertices like the red picture. And the GCN.
Wait a minute.
Oh.
Yeah, you should explain the graph.
Okay, the graph is like the green one, and the red one is hyperedge. It's E1, E2, and E3, and V1, V2, V3 is the vertex is contained by E1, and V2 and V3 is contained by hyperedge 2. So the vertices can contained by different hyperedges, and the one hyperedge can contain multiple vertices. It's about the hypergraph.
So each shaded region actually represents a hyperedge.
Yeah.
And all the vertices inside that shaded region are connected together.
Yeah.
Okay. So yeah, that's one very property of hypergraph is that one edge can connect 3 nodes or 4 nodes or 4
Yeah.
vertices.
Yeah, right.
Okay. Go ahead.
And the graph convolutional network is a old paper from the 2017, and the defined function is a forward model for the simple 2-layer GCN formula used in this paper is about to do the activation function and to times the theta 1 and then to times theta 2 and times a Johnson matrix and then do the softmax. If the main idea is to use the nodes neighbors and the neighbors the information and to represent the nodes, the final represent the information. It's just to put the other neighbors information to back, just do the convolution to these original nodes. And the axis.
And yeah, you should first introduce the notation. What does X mean? What does A mean?
Yeah, I'm going to introduce the axis, the feature data the feature data matrix, and which contains the graph signals here, and the A is a Johnson matrix, and theta 1 here is the input to hidden weight matrix, and the theta 2 is the hidden unit to output weight matrix. And
so X does X contain feature vector for every node?
Yeah.
Graph. So suppose you got n nodes. I mean, you got n nodes in your graph. So assume that X would be a matrix of size n by d. D is the number of features.
Yeah, it should be it.
And what does A bar mean?
A bar is you can think it's a Johnson matrix of the X.
Of A?
Of X.
It's matrix, right? A bar, I guess, is Laplacian, graph Laplacian.
Yeah.
I have a question about the A matrix. So for hypergraph, what's the adjacency matrix defined?
Excuse me?
So for hypergraph, how the adjacency matrix defined? Because for ordinary or normal graph, so the adjacency matrix is just connect two vertices at maximum. So you just put 0 and 1 into the matrix. So for hypergraph, if 3 nodes share the same age, so how the adjacency matrix looks like?
I'm not sure about it.
Right now, Keyan is talking about graph GCN. Is graph convolution. As you talk about.
I got confused. Sorry.
Okay, so
What is the graph Laplacian?
I will talk it later. And yeah, I will talk it later. It's about to use the graph Laplacian and to transfer it to a bar and
But
use
yeah,
it into
A
the
bar is a graph Laplacian, so it's n by n, right?
Yeah.
One is n by n. So you multiply with x, you kind of do some kind of aggregation. You
Yeah.
multiply with a matrix that won't change the row number. You do the ReLU, you multiply A again, you multiply a second level matrix. Okay.
And the ReLU, the activation function can be chosen by others, but this paper use the ReLU one. Yeah.
And here eventually is assuming they're doing like node classification problem, right?
Yeah.
So you got to predict the label of every node in the graph.
Yeah.
Okay.
And use the information from its neighbors and neighbors like that.
Okay.
And it uses for multi-classes is the multi-class classification Q class, and it uses the cross interface function to minimize to train the semi-supervised learning problems. And ZIG is the number from the two-layer GCN results, and the YIG is the label that I think the YIG it doesn't mentioned in the paper, but I think it's represented. It is the expect label from the other unknown nodes.
The YIG should be the one hot encoding.
Yeah.
Since like
the labels.
The label
should be
for
the
I.
labels, yeah.
So it should be like 1000, something like that.
And VL here is a set of label examples. Examples.
Okay. Okay. Yeah, you might just observe a subset of nodes who
Yeah.
have the labels, right? Okay.
And here, this paper proposed a new training method for the SSL on hypergraph, and it has also two variants. One is the first one is the one hyper-GCN and the hyper-GCN, fast hyper-GCN. First, for the one hyper-GCN, the new idea here is to use a hypergraph Laplacian over the simplified hypergraph. So the main idea is to the author use to simplify the hypergraph to a simple graph, and it's here you can see for each hyper G and let's just two vertices, and to argmax the signal I minus signal G, and breaking types randomly, and this step is to find the two vertices that represent the largest signals of each hyper edge. So just to find the two vertices can represent the mostly on the one hyper edge, on each hyper edge. And
so okay, so SI and SG are signals. So are they feature vectors for vertex I and G?
it's just this is just a formula to represent their ideas, not a actual one.
Okay.
Yeah, and F here is defined as the signals, and it's just a symbol. It's not an actual function here. And to find G to represent the one hyper edge, and to convert it to a simple graph, and then to use a weighted simple graph G to construct by adding the weights, the hyper edge weights and the hyperage weights to let add these two and to become the weights of the simplified edges.
So the weights is also defined freely. I mean, you can choose whatever weights.
Yeah, it's the original hyperedges weights. Hyperedges weights.
Yeah, but hyperedge does not necessarily have weights, right?
Yeah, it's defined by themselves.
Okay.
And that's the AS one is the weighted adjacency matrix of G, and the hypergraph Laplacian is this function.
Yeah, it's just about how to compute the Laplacian.
Yeah, the same function.
What does the S mean?
S is a simple graph, is transformed from the hypergraph. It's a simple graph's adjacency matrix. This is a simple graph G, and AS is the weighted adjacency matrix of simple graph. So it's just to convert the hypergraph to a simple graph, and use the simple graph to do the graph Laplacian.
Yeah, my question is, this one is the normalized graph Laplacian, right? Why do they multiply with S? S is any is the feature matrix, right? Or something like, or signal. I know. I'm kind of confused about notation. Why should we have S?
I remember this function can separate by two parts, and one is this one. One is this one total. Oh, this one total, and then times S. But I'm not sure the S represents what does it represent here.
Yeah, S according to your first item, right? S is the signal defined on the hypernodes. So I will it as. So here you're assuming S is S is a vector, right?
Yeah.
Okay, yeah, let us continue.
And the result of this one is the input of the AX here.
So they just replace A bar.
Yeah.
By the LS.
Yeah.
Okay.
What is the Laplacian of normal GCN?
Actually, it's just this one, because this AS is also just a normal graph. It's converted. This is a graph after the converted.
Okay, so what is called the Laplacian? It's a Laplacian transform of something?
Yeah, it's a Laplacian transform from the diagonal matrix and the adjacency matrix and to the Laplacian form.
Okay.
It's just like giving you any adjacent matrix. You can through this formula Laplacian.
Okay.
Okay, yeah.
And we can see in the above GCN progress when applied to a hypernode. And here is from also a 2017 paper, and the neural message parsing, the function is defined as this. This is defined, the HV is the hidden information in the way unit. The hidden information in the hidden unit of the node way, and this is the hidden information of the node U, and tau is the epoch, and the theta is the hidden width.
Okay, so what's the connection between from the previous slides? Previous slides, you just convert.
Yeah, this is
A graph to a normal graph, and then apply the.
this is this function is will show the information changing in each node in its hidden unit, and per epoch.
No, I mean, I go back 2 slides.
Yeah.
I'll go back 1 slide. So here, I'm assuming that, okay, this is a very simple approach that they convert the hypergraph into a normal graph, right?
Yeah.
And then, do they just apply this normal graph with the standard GCN, or
Yes.
they have to continue?
Yeah. They just use the simplified to apply the GCN.
Okay, so what about next slide? Next slide is about another method.
No, it's not. It's not another method. It shows the information change in the per nodes.
So it's just to explain how it's working.
Yeah, and inside. This is the whole idea, and this is how the information change in the per nodes, and the hidden unit, the hidden layer of representative of node void. It's just to show one node to change, one node changing.
Okay, so looks like their A bar S tau. I mean, it will vary along with tau, right? The number of epochs.
Yeah.
How is it possible? Like, because once you convert it into a normal graph, the graph structure will be fixed, right? Why do they change?
What do you mean? Which one changed?
This one, right? So they denote A bar S and with subscript tau, right? So
Yeah.
tau is the number of epochs. So it implies that, okay, tau, this Laplacian graph Laplacian will change along with tau, right? How does it happen?
Can I go back to the previous slide? S change with tau. S is change epoch by epoch.
Yeah, you can only explain as like ES is vary along with the number of epochs, right? How does it change? Yeah, can you show us next slides? Maybe we can figure out together.
Yeah. This one is just For example, it will the one node way and connected by 5 hyperedges, but it can only represent three hyperedges now after the simplified. And this is the actual function they use. They use the L2 algorithm and I will max it and to show the node I and then node G to simplify it.
Oh, so the S here will be this guy, right? Theta transpose HI tau. That's the
Mhm.
signal.
Yeah.
Okay, then it can explain why it kind of dynamic changing, right?
Yeah, this one also has.
So every time, like, suppose you got, yeah, I was confused about how they define their S or the graph signal, like say, this is a hyper edge,
Yeah.
which connects the 3 nodes. So suppose in layer, I don't know, maybe in layer 1, like layer 1 is 1, 2, 1, 3, 2. So they're gonna first multiply with this theta tau, right?
Yeah.
With H1, H2, H3 to get their signal, then compare, then they decide which pair of the nodes have the maximum difference of the signal. Then they build out, then they add an edge, right?
Yeah.
But how many layers do they have? Just 2 layers?
Yeah, just 2 layers.
Then if there's 2 layers, so at the first layer, I mean, in the first layer, the input will be your data matrix, right?
Mhm.
And in the second layer, it will be your representation. Which layer decides the graph structure?
Mm. I think it's a second layer. I'm not sure, but for the second layer and
Oh yeah, okay. Because there's okay, so the first layer is the hypergraph,
yeah,
and you need to multiply with theta to get the signal. And then you can decide the structure in the second layer.
yeah. The second layer is for the outputs.
This is Mikayan. I'm trying to figure out what's the relationship between the message function, the right side, and the signal. Is signal corresponding to the A bar?
You mean which function? This function?
Yeah, it seems like a message function in the graph network. And I want to ask, is there the signal corresponding to A bar? Is that correct?
Yeah. Yeah, because you can see the graph, and this function is just like the graph shows from the other nodes information and to convolution into the node way here.
Okay.
And
thank you.
like for example, this is way and this is u, and here this one is the information for u. And this A bar is a weight of these two.
I think that A bar is the edge in the graph, and the edge is the every node.
Yeah,
right?
each is every node, but here is, for example, just the u and v here. It's just 2 nodes. but generally it's just V and U, but actually it will calculate all the.
Okay, thank you.
Yeah, because it's a set. The N is the set.
Yeah, I'm confused here. Like, to me, like tau is more like layer number, not epoch number.
I think the tau is the iteration in the graph.
How they define a rule like to compute each tau, to update each tau. It's just update like this. It's not a gradient based approach. It's just a. Can you go back, go to the next slide?
And the next one is the hyper GCN. And you can see the disadvantage of the one hyper GCN because it used two nodes to represent one edge, but so other nodes will be ignore. And here, just for hyper GCN, it will reuse these ignored nodes as mediators, and to use the information as weights in this ignored nodes. And here, just for the weights of each mediator edge, you can see here is 2 times number of vertices minus 3. Because you can see if we have 3 vertices and 1, 2, 3, and we have 3 edges, and the sum is 1, and just to divide by the number of edges, it's weight of each edge, and it's the weight it is a weight of the connecting the mediators.
So the mediator, so the mediator is some virtual node.
Yeah, it's not an actual nodes, but it's use other ignore nodes. For example, if we one hyperedge has 4 vertices, and we just choose 2 to represent it, and so we have 2 mediators. And
Do you mean the remaining nodes are mediators?
the ignored nodes.
The ignored nodes are viewed as mediators.
Yeah.
Oh, so each ignored node will connect to the both represented nodes.
Yeah,
Okay.
correct.
And they assign a weight by 1/2 size of hyperedge subtracted by 3.
Yeah. If we have 4 nodes, 1, 2, 3, 4, and we have 1, 2, 3, 4, 5. So 2 times 4 minus 3 is 5. It's just mathematical.
All right, just want the 2 times the size minus size of E minus 3 is just the number of the additional edges.
Yeah.
Okay. Yeah, let's stop here temporarily. Like we can continue from 12 I think 12:40. Yeah, we'll return at 12:30. I won't close the Zoom. Yeah. So after that, just to connect back. Right.